And we went through, it wasn't a complicated process, but you had to be kind of creative about figuring this out. And the question was, what is the base A logarithm of B over C? And after doing some work, we determined that the answer was 3.5. Okay, and I want to just leave that up there, and we won't worry about how we got that. It wasn't even that set of numbers, I don't think. But I want to leave it up there so I can come back to this a little bit later. Because this is a problem that I said, if we knew the laws of logarithms, you could find the answer to this question just like that. There's nothing to it. Okay? So, just as we have exponential laws, we also have logarithmic laws. So we have rules in mathematics that govern how we treat exponents. Since logarithms are exponents, it probably shouldn't surprise you that there are rules for how we treat logarithms. And there's what we call the product law, the quotient law, and the power law. We have those in exponential laws. We have similar laws in logarithmic. And we're going to be using these laws today. So what is the product law? What is the product law? The product law talks about how you treat the logarithm of a product. It's important for you to understand we are not talking about the product of logarithms. We're talking about the logarithm of a product. And it says when you take a logarithm, a base B logarithm, B can be any allowable base, greater than 0 but not equal to 1, of a product of two things, instead what you can do is add the logarithms of each of the factors of those two things. So instead of saying log of 10 times 20, we can say log of 10 plus log of 20. This is how a slide rule works. Remember me talking to you about a slide rule? Because when you line up the two rulers, you're really just adding spaces. So you're finding out what products are by addition. There's a quotient law, which says the logarithm of a quotient is one thing divided by another, is the logarithm of the numerator minus the logarithm of the denominator. Now, does the order in which you multiply two things matter? No. Does the order in which we add these two logarithms matter? No. But when you divide things, does the order of division make a difference? Does it affect the answer? Yes. 12 divided by 3 is 4. 3 divided by 12 is not 4, it's 0.25. And the point I want to make is, when you're applying the quotient law, it must be the logarithm of the numerator minus the logarithm of the denominator. And one little seed I want to plant in your head right now is it means this. Anything that is in the denominator will have a negative in front of the logarithm because you're subtracting that logarithm. Anything that is in the numerator will have a positive. That's an important kind of idea, then I'll come back to that. And then the power law, the most powerful one, no pun intended, it really is. It's such a valuable logarithmic law. Says when you take the logarithm of a power, m raised to the n is a power. A power has a base. In this case, the base is m, and it has an exponent, which is n. When you take the logarithm of a power, you can instead just take the exponent times the logarithm of the base. And it's an incredibly valuable thing. So let's get started with some examples. Write each expression in terms of individual logarithms of x, y, and z. This is going to have two steps, but after looking at this example, for most people it's going to have one step. So the first thing I do is I say I'm taking the logarithm of a product. I've chosen not to put brackets around some of my typed work because it very often isn't written that way. But that set of brackets is important. You understand that x squared y is the entire argument of the logarithm. So all I'm doing is saying, since it's the logarithm of a product, I'm writing it as the sum of the individual logarithms. And then log base 3 of x squared, and I should have a 3 here, log base 3 of x squared is 2 times log base 3 of x. And what I'm saying, what I said to begin with, is I think it's a simple matter to go from the top to the bottom here. Would you agree? In fact, if I look at b here, this is going to be log base 6 of x minus 3 log base 6 of z. Because it's a logarithm of a quotient, it's logarithm of the numerator minus logarithm of the denominator. And again, I'm not going to say it every time, but this set of brackets around the z cubed is not necessary. But I want to impress on you that you're only allowed to move that exponent down in front with the power law if that exponent is part of the argument. Okay? So now I can move this 3 out in front. Are we okay with A and B? Yes? Okay. So what about this one? Well, this would be log base 2 of xy cubed minus log base 2 of z squared. It's the logarithm of the numerator minus the logarithm of the denominator. But now this first logarithm is a log of a product, so this is log base 2 of x plus log base 2 of y cubed minus log base 2 of z squared. And I've dropped the brackets only to get you accustomed to the fact that sometimes they're there and sometimes they're not. We can move all of the exponents in front, so we'll have log base 2 of x plus 3 log base 2 of y minus 2 log base 2 of z. Really pretty simple, but it doesn't mean the applications of this are going to be simple. We're just warming up to stuff here. Any questions with C? Okay. So this one. Let's go back to C. How many of you feel as though you could go from this point directly to that? I hope everybody. There's not much involved here thought-wise. So if you do that, and you write this as log base b of x to the 4, which is 4 log base b of x, and then you go minus 10 log base b of y plus 3 log base b of z. Are you with me on what I've just done there? It's wrong. Does anybody want to take a stab at why this is incorrect?
You need brackets.
I need brackets around this. Because, and I'm going to show you a shortcut that saves us a lot of time. But the reason for that is this is log base b of x to the 4 minus log base b of y to the 10 z cubed, right? It's minus that logarithm of a product. And that logarithm of a product is a sum of logarithms. So when you're subtracting a sum, you have to subtract the entirety of the sum. You can't just subtract part of the sum and then add the other part. You have to subtract the whole thing. So the result is going to be that what you end up with is 4 log base b of x minus 10 log base b of y minus 3 log base b of z. And right at the beginning of the lesson, I said, when we talked about the quotient law, which is what we're applying for this initially, I said that if you have something that's in the denominator, the logarithm will be negative. So y to the 10 is in the denominator, which means the logarithm associated with it is negative. Z cubed is in the denominator, so the logarithm associated with it is negative. It's just a quick shortcut. Because if there's 4 or 5 different parts or variables, then it gets complicated with the brackets. What about this one? Well, I'll just throw the question to you. How many of you feel as though you would be able to just write that? So you have to be able to see or know that x, the cube root of x is x to the third. The square root of y is y to the half. So this is going to be log base 7 of x to the third minus log base 7 of y to the half, and then those exponents go in front. I feel as though you feel this is easy so far. You're following it, and that's good. Okay. Use the laws of logarithms to simplify and evaluate each expression. So we're not going to evaluate this by using any advanced features on the calculator. We're going to simplify this and hopefully use our brains to get an answer. This is log base 2 of 40 over 5. Because the difference of logarithms is a logarithm of a quotient. And 40 over 5 is 8. And log base 2 of 8 is 3, because 3 is the exponent to which you raise 2 to get 8. If we write this as a single logarithm, it's going to contain a factor of 45 in the numerator, a factor of 15 in the numerator, and a factor of 25 in the numerator. So that's what we are left with. I mean, I guess you can use your calculator to simplify this. You could also, divide 45 by 5 and 25 by 5 and start reducing it down. We're going to have 9 and 3. So do me a favor and work out what that new argument is going to be. That's 3 and 5. It's going to be 27. I mean, you could figure it out by canceling some 5s and going from there. But this is log base 3 of 27, which you should know like the back of your hand at this point in time is 3. I think maybe even log base 3 of 27 is 3 without even thinking about it, possibly. It's the exponent to which you raise 3 to get 27. Which is 3. So what are we going to do with this? I'm intentionally trying to confuse you. I don't think it's wise to figure out what this is and then worry about subtracting. Because if you figure out what this is, it's going to be log base 8 of 3. I guess you could do that, but it's not always going to work out that way. It might work out to a bunch of fractions somewhere. So what I would do is say to myself, this is log base 8 of 48 plus log base 8 of 4 minus log base 8 of 15 plus log base 8 of 5. Because when I distribute that negative, the negative log base 8 of 5 becomes positive log base 8 of 5. You can feel free to simplify what's in brackets, and it would be okay here only because 15 divided by 5 is a nice number. But if it weren't, then this is the better strategy. So now I can say that this will be a single logarithm. It will be a base 8 logarithm. 48, 4, and 5 will be in the numerator, and 15 will be in the denominator. And I think that's going to work out to 64 as an argument. Pretty sure. So this is log base 8 of 64, which we should know is 2, because 2 is the exponent to which you raise 8 to get 64. D, this is going to be a single logarithm. of 7 times 9 times 1/3. And 9 times 1/3 is 3. 3 times 7 is 21. So log base 21 of 21 is 1. However, what if I said, figure out the value of this? Would you get a different answer? You'd get the same answer, wouldn't you? Because we're going to have a single logarithm. It's a base 21 logarithm. We'll have in the numerator 7 times 9, and then in the denominator 3. Now, why is that? I mean, I'm not saying why are these things equal. You know times 1/3 and divided by 3 are the same thing. But why does that work? The reason it works is because this log base 21 of 1/3 is log base 21 of 3 to the negative 1. 1/3 is 3 to the negative 1. But I can use the power law here and move that negative 1 out in front. And what I'm telling you is a rule. It's actually a law, but it's not given to you on a formula sheet. I call it the negative logarithm law, that if you have the logarithm of a fraction, you can flip that fraction over and change the sign of the logarithm from plus to minus or minus to plus. You can even do that with the base. If you have a fractional base, you can flip it over and change the sign of the logarithm out in front. It makes life very easy. Anyway, the answer is 1. E. Well, we can't pack these two together as a single logarithm until we bring those exponents up. So we're doing the exact opposite of what we did in the very first example, where we separated the logarithms, then moved the exponents down. Now we move the exponents up and bring the logarithms together. So this is going to be the log of, well, 5 squared is 25. Times 20 squared is 400. Along the way, I'm trying to teach you some common sense math. 25 times 4 is 100. Add 2 more zeros and you get what this argument is. It's going to be 100 followed by 2 more zeros, so it's 10,000. You can feel free to confirm that on your calculator. So what is the logarithm of 10,000? It's equal to 4 because this is a base 10 logarithm. And it's saying, to what do I raise 10 to get a 1 followed by 4 zeros, which would be 4. And again, I want you to resist the temptation to go to your calculator and use a change of base formula or use your log base function and just enter it all in to get an answer. I'll just ask the question, how many of you see that this is equal to 0? It's equal to 0 through 3 strategies. One, you can move this 3 out in front and have 3 log of x minus 3 log of x. I think it's pretty clear that that's 0. 2, I can move this 3 up in front instead and have log of x cubed minus log of x cubed. I think it's pretty clear that that's 0. I could write this as log of x cubed over x cubed, because the difference of logarithms is the logarithm of a quotient. And that gives us log of 1, which is 0, because this is a base 10 logarithm, and it is asking you, to what do you raise 10 to get 1? And the answer is 0. I just want to go back and look at something here, though. No, we're good. So now let's take a look at this next one. Write each expression as a single logarithm and state the restrictions on the variable. Well, this is going to be log of xz over y. Correct? Not x over yz. The log of z is a positive logarithm, so it goes on the top. In other words, this could be written as log of x plus log of z minus log of y. So log of x plus log of z is log of xz, and then the minus log of y goes in the denominator when you put it together. Are we okay with that? Okay. What are the restrictions? Okay, so we haven't really talked about this yet. X must be greater than 0. These are base 10 logarithms, so just using the base 10 button on your calculator, what is the logarithm of 0? You can't do it, right? You get an error. Why do you get an error? Because if I said to you, what is the log of 0? This is A, this is the answer, this is what we're trying to find. Then I'm saying B, which is a non-zero number, raised to what we want to find, is going to give you nothing. And you cannot get nothing by taking 2 to a number, or 3 to a number, or 1/2 to a number. You will always get a number that's bigger than 0, which means you can't take the logarithm of a number unless it's bigger than 0. Similarly, if I said, what is the logarithm? It doesn't matter, base 2 logarithm of -8. I'm asking you, to what do you raise 2 to get -8? And 2 raised to an exponent will never give you a negative. And now I'm telling you officially that the argument of a logarithm must be greater than 0. That's always the case. So x has to be greater than 0, y has to be greater than 0, and z has to be greater than 0. And we look at the original expression. We don't worry about the expression afterwards. Well, this is going to be log base 2. We have an x which will go on the top because it's a positive logarithm base 2 of x. We have a 2x that will go on the top. We have an x squared that will go on the bottom, and we have a y that will go on the bottom. By the way, I hope you see that x and y must both be bigger than 0, because they're arguments of logarithms. So we can simplify this and get log base 2 of 2 over y. Because in the numerator of that we get 2x squared, but we have an x squared in the denominator, it cancels. So now we start to get a little peek at where this can go. That if I gave this to you on an exam as a multiple choice question, I would not have that as a choice. What I would have instead is the following. Why is that? Well, because log base 2 of 2 over y is log base 2 of 2 minus log base 2 of y. Notice, by the way, how I keep things nicely lined up. The 2 and the y and the words log are all on the same line. So I've applied the quotient law to this, and log base 2 of 2 is 1. So I can write 1 minus log base 2 of y. It's not quite the same idea, but it's along the same lines as getting a trigonometric answer and then, recognizing it can be written in different ways. By the way, it's a base 10 logarithm. I hope everybody sees that that's what it's equal to. because that exponent, I'm even calling it an exponent. That coefficient of a half goes up as an exponent on the y, so the argument of that second logarithm is y to the half, which is root y. And you're adding the logarithms, so you multiply the arguments. And the 3 goes up as well. X and y both must be greater than 0. One final question, right? Okay. As I said, it's not a long lesson. What is this equal to? Well, to begin with, it's not a big deal to write what this is equal to. It's log of a times a plus b over a minus b. I don't really need that set of brackets on the bottom. And you cannot cancel anything here because what you have on the top are exactly 2 factors. Those are the 2 factors on the top. You can only cancel if you see a factor on the top that's identical to a factor on the bottom. And you have a different factor on the bottom. This is like me asking you, can you simplify that? The answer is no, you can't. That's not what makes this problem unique. What makes this problem unique is what are the restrictions? Well, we start off by saying that this argument must be greater than 0. No question about it, right? A must be a positive number. And then we say a plus b must be a positive number. So what does that mean? It means that a, which is already positive, plus whatever b is, must also give you a positive. And then we have a minus b must be positive.